Hello there. Welcome to another edition of Mr. Weis Solves an Old AP Problem. Today we are doing the 2013 AP Calculus BC problem number 2. Please ignore all of the boxes that you're seeing off to the right here. I just unpacked my tent and that's the boxes that came with it. I'll be cleaning them up eventually. So there you go. So what is this problem all about? This is a polar function problem. So it starts out by giving us two polar functions, r equals 3 and r equals 4 minus 2 sine of theta. They provide the graphs for us, which I've kind of done a little bit of a crappy job drawing. Hopefully you realize that r equals 3 is the circle. This is the set of all points that are a distance of 3 from the origin. That's what r means in the xy plane. And this is in fact the xy plane that I've tried to draw here. This is x, this is y. Theta, on the other hand, is the angle that's swept out from the positive x-axis, known as the polar axis. And the other graph is this, it's a cardioid with kind of like a little bump right there that kind of goes around like this, r equals 4 minus 2 sine theta. Now, they've been kind enough to tell us that these two curves intersect at the angles pi over 6 and 5 pi over 6. So you can see my picture is not drawn very much to scale. That looks more like pi over 4, but it's actually pi over 6. I think it's kind of cheap that they gave us this answer because we could have found it ourselves. And in our class, I would have required you to. You would have found that by simply setting the r's equal to one another here, and you would have had to solve a trig equation, and you would have found that theta equals pi over 6 and 5 pi over 6. So what does part A ask us to do? Part A wants us to find the area that are contained in both of these at the same time. So it wants that area right there. So that's what we're going to find. And this is a calculator ready or calculator allowed problem, so at some point I'm probably going to break out my calculator and use it here. So okay, we want to find the area, the green area in this picture. So the way I would do this is I would split this into two areas in an interesting way. So this angle right here is pi over 6, this angle right here is 5 pi over 6. If I only look along this part right here, like this is, that area right here is actually the area of a sector of a circle. No integral is required. All I need to know is what this angle right here is. That's the only thing that is in question, is what is this angle right here. Well, that's easy to figure out because this part right here is pi over 6 and this part right here is also pi over 6. This bottom half of the circle is pi, so it's pi plus 2 pi over 6, so pi plus pi over 3, so 5 pi over 3. So this angle right here is 5 pi over 3. And the area for a sector of a circle, is 1/2 r squared. R in this case is 3, so 3 squared theta. Theta in this case is 5 pi over 3. Plus, now I have to find the area of this other bit, and that is a little bit harder. This one will require an integral. So what I'm basically going to do is all polar areas, you remember, are taken from the origin and work their way out. The way we came up with these formulas is using the formula for the area of a sector, in fact. So basically I want to start at the origin and I want to shoot out to the cardioid curve. And I want to do that during this entire region right here. And so that's the second half. I'm actually going to use, whatever. It's a calculator, so I'm not even going to bother to use symmetry, but I might have used some symmetry here. So for the second one, that's the area of this little bit right here. Looks kind of something like that. That is 1/2, there's always a 1/2. The integral from pi over 6 to 5 pi over 6. Of r squared. R in this case, it's same, right? R squared, it was that one. R in this case is this curve, so it's 4 minus 2 sine of theta squared d theta. And there you have it. So now I'm simply going to figure out what this is. So I don't know, I'll simplify some things. So what is this? That's 9, that's a 3 in the bottom, they're going to cancel. So I think I just get 15 pi over 2 plus, and then we have to do this integral. Small error. This shouldn't have been 5 pi over 3. This is 4 pi over 3. Pi plus 4 pi over 3. Pi plus pi over 3 is 4 pi over 3, not 5 pi over 3. 4 pi over 3. So this ends up becoming, so there's still a pi that cancels, a 2 cancels. So I think we get 6 pi plus. Alright, and now I'm going to break out my calculator to do this integral. So 0.5 times math 9. We're doing the integral from pi divided by 6 to 5 pi divided by 6 of 4 minus 2 sine of x quantity squared dx. Come on. And I hit enter. I get 0.589 5.89, gosh, 5.8592 approximately. So plus 6 pi, and I'm getting approximately 24.709. And that is my final answer. Welcome back. I had to come move inside because there's some construction going on outside and it was just too loud. So here we are inside my den, kind of. Hopefully the picture isn't so bad. So we're working on 2013 problem number 2. And this part we're just dealing with the cardioid part of the curve. So we've got r equals 4 sine of theta. The graph of this thing is over here. And this is actually a motion problem. So they're telling us that a particle is moving along this curve so that at any time t, the angle that you would plug in to figure out where the particle is theta equals t squared. So for example, at time 0, I would plug in over here, I'd get theta equals 0, and that puts me right there. So at the beginning of time, the particle starts right there. At time 1, if I plugged in 1, I'd get 1 squared for theta, which is still 1. That's 1 radian. 1 radian's about 60 degrees, so that would put me right there. At time equal the square root of pi over 2, I would plug in t equals the square root of pi over 2, and theta would end up equaling regular old pi over 2, which would put me there. At time root pi, note that that's still less than 2, by the way. That's still less than t equals 2, the square root of pi is less than 2. I end up being here. And at t equals 2, we'd end up getting theta equals 4. I don't know, that's somewhere like down here somewhere. It's probably like right around here. Here we are at t equals 4. Okay, so what is the question asking? I don't know. Oh, here it is. Here's my iPad. So what is the question asking? It's saying, find the time t on the interval from 1 to 2 for which the x-coordinate of the particle is in position -1. So we want to know, when is this particle at position -1? So it looks like that happens right here, and it also happens down here, but that looks like that might be outside of the range of values that we have. We're only going from t equals 0 to t equals 4. So that's what it's asking us to find. Okay, well that's easy. The x-coordinate of the particle at any moment in time, well, the x-coordinate as a function of theta is equal to r cosine theta. So in our case, that's going to be 4 minus 2 sine of theta times cosine of theta. And we want the x-coordinate to equal 1. So what we can do is we can find out when this equals 1. That'll give us a theta value, and then we can plug that in and figure out what t is. So that is what I'm going to do. We could also plug in, given that theta equals t squared. We might as well do it all at once. I could plug in, given that theta equals t squared. X as a function of time, then, is really just 4 minus 2 sine of t squared times cosine of t squared. And basically we want to know when does this equal 1 on this range right here. And one of the reasons I like plugging in t is that now I know what range I'm looking at, whereas for theta I wasn't really sure. I guess theta goes from like from 0 to 4 actually, so I kind of would have known what theta does too. Okay, so here we go, plugging this into my calculator. Now how am I going to do this? I'm going to plug y equals, I'm going to plug in not in polar mode, I'm going to plug in this function here. I guess I'm going to have to use x for t. So it's going to be 4 minus 2 sine of x squared all times cosine of x squared. That's going to be y1. y2 is going to be the function, the value 1. Now before I hit go, I'm going to go to my window and I'm going to realize that the role of x is being played by t here, and we are only interested in t going from 1 to 2. So my x min I'm going to make 1 and my x max I'm going to make 2. Then we have to realize that what the y stands for in my calculator is actually the x coordinate of this particle. And I can see that from time 1 all the way up to time 2, by the way this was time 2, I don't know why I put 4 there, this is time 2, I can see that the biggest that the biggest that the x coordinate is looks like it's around 2, and the smallest that the x coordinate is negative 4. So I'm going to have my y therefore go from negative 4 up to 2, and then I'm going to hit graph, and I should see something kind of nice. Right now it's graphing the x function. And then, oh, I don't want it to equal 1, I want it to equal negative 1. So again, I keep on messing up. This is when does it equal negative 1. And then I'm going to calculate the intersection. So, second, calculate, intersect, first curve, second curve, guess. And I found out that this happens when x, but in my calculator, don't forget, x is actually t. T equals 1.428, approximately. 1.428. And that is my final answer. Okay, welcome back. Here we are doing 2013 problem number 2 from the AP Calculus BC exam. This is a polar function with a little bit of like motion sort of built into it. So in part B we were dealing with this dimpled cardioid, and we have a particle that's moving around this dimpled cardioid, so that at any time t you can find where it is on the cardioid by plugging in that time into the theta equals t squared, figure out what theta is at that time, plug it in over here, and boom, you can find out where you are. So we had drawn a couple of things. We knew, for example, that at time 0 we were right there. At time 1 we were right here. At time the square root of pi over 2 we were right there. At time the square root of pi we were right here. In fact, we found out that in part 1 we found out that at time approximately t equals 1.4 something we ended up being right here, having an x coordinate of negative 1. Now what it wants us to do in part C is to come up with a vector valued function that describes the position of this particle at any moment in time. So that's what we're going to do, come up with a vector valued function that describes the position of this particle at any moment in time. I'm going to call this vector valued function p of t, p for position. So p of t, well, let's see. At any moment in time we need to know what its x and its y coordinate are, but this is a polar graph. So the x and y coordinate are given by, the x coordinate is r cosine theta, the y coordinate is r sine theta, but we want this all in terms of t's. So we're going to get r, so that's 4 minus sine of t squared, times cosine of t squared, that's the x coordinate of the particle, and the y coordinate is 4 minus sine of t squared times sine of t squared. And this describes the position of the particle at any time t. The thing that they wanted us to then compute is, what is the velocity of the particle at time 1.5? So they want the velocity of the particle at time 1.5. So the velocity of the particle is the derivative of the position of the particle. It's a vector. The velocity is a vector. It is no longer the slope of a tangent line because we have a particle moving in two-dimensional motion, and we're interested in both the direction and the speed at which that particle is moving. So in this case, it's going to be the derivative of these things right here. So I'm going to have to take the derivative of each one of these pieces, d dt of that, and d dt of that. And then what I'm going to do is plug in t equals, I believe they wanted 1.5. Yeah, they want v of 1.5. So I'm going to end up doing basically all this in my calculator. I do not want to do these things by hand, so I'm going to do this all in my calculator. And so here's how I would do it. I've actually already put into my calculator the x coordinate. I put that in as y1 for something we were trying to do in part B. So that's y1. So what I'm going to do is I'm going to do math n derivative, math 8, of, with respect to x, of y1. And I want to do that at 1.5. And I end up getting that this is, the first component is approximately negative 8.072. This is approximate. And now I want to do the same thing, but I want to do it with the y coordinate. So I'm actually just going to go back into my y1, and I'm going to change the cosine to a sine, and quit out of there. And then I'm going to literally ask it to do the exact same thing I did a second ago. And this is negative 1.673. So let's see if this makes sense. It looks like my velocity at time 1.5 has both the x and the y coordinate being negative. Now, we found out earlier that at time 1.4 I was right here. At time 1.5 I must be over here somewhere. I'm probably over here somewhere. And my velocity vector looks something like this, where you can see that the x coordinate is changing a lot, getting very, very more negative. But the y coordinate is not changing as much at that time. So I suspect that I'm somewhere like right here at time 1.5 approximately, and this velocity vector makes sense given that. And that's my final answer.